In this video, we're going to be looking at the solution to a special type of differential equation called a separable differential equation. Previously, we've looked at the solution to a differential equation through a directional field and Euler's method. Now we're going to be looking at the solution analytically. A separable first-order differential equation is in the form dy dx equals an f of x times a g of y. And these can be separated into a function of x and a function of y. So if we have dy dx equals g of x times f of y, and it doesn't matter if it's f of x times g of y or g of x times f of y, we can rewrite this by letting h of y equal 1 over f of y, and then we can separate our variables. We can get all the y's on one side and all the x's on the other side. And if you want to think about it this way also, we can leave it in the original form. We could leave it just like this form right here. If we have dy dx equals a g of x times an f of y, we still can separate them this way. Dy all over f of y equals g of x times dx. Now it does look like we're just multiplying the dx over on the other side, but we're rewriting this in differential form. Now we can take the antiderivative of both sides of this equation and we can solve this differential equation. We could solve for y in terms of x. We can't always necessarily solve this explicitly because we may have combinations of algebraic and trigonometric functions, but if possible, we do try to solve for y explicitly if the equation allows. Let's take a look at an example. Solve the differential equation. Now this is a differential equation, a separable differential equation, because we can separate our variables. We can get all of the y's on one side and all of the x's. And again, this is writing the equation in differential form. We studied differentials a while back where we had dy equals f prime of x. Instead of writing dy dx, we wrote it in differential form. This is called the differential form. Let's continue solving this differential equation. Now that we've separated our variables, we can take the antiderivative of both sides. Taking the antiderivative, we'd have 2y squared over 2. We are taking the antiderivative with respect to y, and then plus the sign of y. On the right side of the equation, we would have 6x cubed over 3. We could put a plus c on the left side of the equation and the right side of the equation, but then we could combine those together. So we're only going to put the constant of integration on one side. If we simplify this a little bit, we would have the solution to our differential equation. We cannot write this one in explicit form. We can't solve for y, so we would leave it like this. We are given an initial condition, so we can solve for our constant c. The initial condition indicates when x is 1, y equals pi. So let's plug in pi for all of the y's. And we're plugging in 1 for all of the x's, and now we can solve for c. Now the sign of pi is 0, and let's subtract, this is just going to be 2, so we're going to subtract 2 to solve for c. Now we have a particular solution. Because we were given an initial condition, we can now find a particular solution. So our particular solution is y squared plus the sine of y equals 2x cubed, and now we can plug in c, which is pi squared minus 2. That's our particular solution to this differential equation. Solving this differential equation using separation of variables, I'm first going to rewrite y prime as dy dx, and then we'll separate our variables. The left side of the equation we could write as 1 over y times dy, taking the antiderivative of both sides. The left side, the antiderivative of 1 over y, we are taking it with respect to y, would be ln of the absolute value of y equals x cubed over 3 plus our constant of integration. And again, I'm going to just combine both constants of integration on one side, the right side. We can put in explicit form. We can solve for y. We're going to raise each side to the base e. That would give us the absolute value of y equals e to the x cubed over 3 plus c. Now I can take the positive and negative, let's move up here. To solve for y, I can now take the positive and negative of the right side to get e to the x cubed over 3 plus c. We can rewrite, if I have something like a raised to the b plus c power, I can rewrite this as a to the b times a to the c power. I'm going to use this property right here to rewrite this one as times e to the c. And then I'm going to switch the order. This piece right here, this factor, is just a constant. It's just a coefficient to e to the x cubed over 3. And typically what we do in this situation is we let a equal this plus or minus e to the c. It's much easier to work with now. So this a contains our constant. If we were given an initial condition, we then could solve for a, and we don't have to deal with a plus or minus. This is our solution to the differential equation. Revisit the circuit problem we looked at earlier, and we solved this using a directional field and Euler's method. We're going to try to solve this analytically this time. So let's plug in the given information to our differential equation. We have R equals 12, L equals 4, and the voltage is 6. So let's plug those values in. We'd have 4 times di dt plus 12 times I equals 60. Let's solve for di dt. If we subtracted 12i from both sides and divided by 4, we would have 15 minus 3i. Now at this point, it may not look like a separable differential equation. However, if we were to rewrite this in differential form, we could rewrite it as di divided by 15 minus 3i equals dt. Therefore, we are able to separate our variables and solve this differential equation. Let's take the antiderivative on both sides. Now, if we used u substitution for this integral, we could let u equal 15 minus 3i. So du would equal negative 3 di. And we don't need that negative 3, so let's divide that. And now we can rewrite this integral in terms of u. We would have negative 1/3 1 all over u du. And the antiderivative would be the natural log of the absolute value of u. So we have negative 1/3 times the natural log, and our u, let's plug that back in, is 15 minus 3i. So we have our 1/3 times the natural log of the absolute value of 15 minus 3i. And now we're going to be looking at this side of the equation. We would just get t plus c. This is the antiderivative of 1 dt. So the antiderivative would be t plus c. Let's multiply both sides by a negative 3. We're going to raise each side to the base e. We would have the absolute value of 15 minus 3i equals, and we're going to use that rule again where we can separate these as e times negative 3c times e to the negative 3t. Then we'll take the positive and negative value times our e to the negative 3t. And again, we're going to let a equal this plus or minus e to the negative 3c. We're just going to replace it with a. So we would have 15 minus 3i equals a e to the negative 3t. We can solve this equation explicitly for I, so we're going to subtract 15 from both sides and then divide by negative 3. So if we subtract both sides by 15 and then we will divide by -3. So I'm going to rearrange the order because this would give us a positive 5, and then we'd have a minus a over 3e to the -3t. We could actually solve for a in this problem because in this circuit problem, if you'll remember, we had an initial condition. At time 0, the current in the system is going to be 0 also. That will allow us to solve for a. I like to go back to the first step that I plugged in a and solve for a at that point. So if I plugged 0 in for I and 0 in for t, at this point we would have 15, and minus 3i would go to 0, equals a. E to the -3 times 0 would be e to the 0, so that would be just 1. So a equals 15. If we plug that in, we have I equals 5 minus 15 divided by 3, 5, e to the -3t. There's the solution to our differential equation. The limit of I of t as t goes to infinity, if we took the limit of I of t, e to the -3t as t goes to infinity would go to 0, because e to the -3t is really 1 all over e to the 3t. So we can see that goes to 0. So we would be left with 5. And we discussed this in a prior video that that limit does equal 5. But now we're showing it analytically. Orthogonal trajectories. We've studied orthogonal trajectories in the past, but in the past we were looking at showing that two equations were orthogonal trajectories of one another. But now we're going to be able to find orthogonal trajectories to a given equation. We're given an equation x equals k y squared. This is asking us to find the orthogonal trajectories to this equation. We know that orthogonal trajectories, the points of intersection, they intersect at a 90-degree angle. Let's find the derivative of this equation first of all and look at the slope of the tangent lines. If we took the derivative implicitly, we'd get 1 equals, we're taking the derivative with respect to x, so we'd have 2ky times our y prime. So y prime equals 1 all over 2k times y, which is the same as dy dx equals 1 all over 2k times y. Let's try to replace k in terms of x and y. If we go back up to our original equation, we can solve for k by dividing both sides by y squared. Let's replace k with x over y squared. And we can see this would simplify to dy dx equals 1 all over 2x divided by y which is equivalent to y divided by 2x. That represents the slope of the tangent lines to this curve of x equals k times y. The equation that we're looking for that has the orthogonal trajectories to this equation, the slope of the tangent lines for that equation would have the negative reciprocal of this equation. So we know that the orthogonal trajectories would have this for the slope of their tangent lines. If we can solve for y, that would give us the equation that has the orthogonal trajectories to our given equation x equals ky squared. This is just a separable differential equation. So let's separate our variables. We'd have y dy equals negative 2x dx. Take the antiderivative. Y squared over 2 equals negative 2x squared over 2 plus our constant of integration. And if we simplified this a little bit, we'd have minus x squared plus c. And I'm going to add the x squared because in this form it looks familiar. That looks like the equation of an ellipse. So this equation of the ellipse has orthogonal trajectories with this equation here. There, the x equals ky squared are the hyperbolas opening up along the x-axis, and you can see the ellipses that we found the equation for just now. These do represent family of curves because we had that plus c. We had x squared minus, plus y squared over 2 equals c. So we do get a family of curves. Another type of problem we can solve using differential equations is called a mixing problem. A tank contains 20 kilograms of salt dissolved in 5,000 liters of water. So we have, let's say, a big fish tank. So we're going to label this. It has 5,000 liters of water, and it contains 20 kilograms of salt. So brine that contains 0.03 kilograms of salt per liter of water enters the tank at a rate of 25 liters per minute. So we have water coming in that contains brine. It's coming in at 25 liters per minute with 0.03 kilograms of salt per liter. The solution is kept thoroughly mixed and drains from the tank at the same rate. So now we're going to show that we have it exiting the tank at 25 liters per minute, but we don't know the concentration because water coming in at 0.03 kilograms per liter mixes with 5,000 liters that has 20 kilograms. And if you looked at the concentration of the tank before the water comes in, they do not have the same concentration. So the water leaving the tank, we don't know what the concentration of that water would be. How much salt remains in the tank after half an hour? Now this is a rate of change. We're looking for the rate of change of the salt with respect to time. Now we know that to find the rate of change of salt, we would have to look at the rate in minus the rate out to determine the amount of salt left in the tank. To determine the rate coming into the tank, it's coming in at 25 liters per minute, I believe it was. 25 liters per minute. And the concentration is 0.03 kilograms per liter. So that would be the rate that the salt's coming in. And you can see if you did the unit analysis here, the liters would reduce and you'd be left with kilograms per minute, the amount of salt coming in. Now we're going to subtract the rate going out. And it's going to be the same thing as what we have here, except here it's coming in at 25 liters per minute times the concentration. We have to subtract off the rate in liters per minute that it's leaving times its concentration. So it is leaving at 25 liters per minute. Now the concentration, to determine the concentration, let's say we wanted to know the initial concentration here. If we wanted to know the initial concentration, and the units are kilograms per liter, we would take 20 kilograms over the number of liters. This would give us our kilograms per liter. That's the initial concentration, but the concentration is changing as it comes out, because this concentration is different than this concentration of 0.03. But we're going to still calculate that concentration the same way. It's the amount of salt, we don't know what that is, divided by the 5,000 liters of, and this would be kilograms per liter. There's our differential equation. If we simplified this a little bit, we'd have ds dt. Now if we have 25 times our 0.03, that would be 0.75, and the units here would be kilograms per minute, minus, and then we have our 25 times S all over 5,000. Again, this would be kilograms per minute. So that's the rate of change of the salt. And we can simplify this. We could reduce here and get our common denominator. So if we reduce and find our common denominator, we would have 150 minus our S, and I'm not putting S of t, it would be the amount of salt as a function of time, but I'm just going to leave it as S, all divided by 200. Because this quantity right here would be 1 all over 200. Then when we got our common denominator, we have to multiply 0.75 times 200, which is 150 over 200. So there's our differential equation. Now the solution to this differential equation, y equals, would be the amount of salt in the tank at any particular time t. So if we can solve this differential equation here, we can find the amount of salt in, it says 30 minutes or a half hour. Let me rewrite our differential equation. We're running out of room here, and I don't know that we could finish it, so I'm going to erase this up here to give us a little bit more room, and then rewrite what we have as our differential equation. So we have ds dt equals 150 minus S of t all over 200. Solving our differential equation, this is a separable differential equation. So we'd have ds 150 minus s equals 1 all over 200 dt. It is a separable differential equation. Taking the antiderivative of each side. Now the left side is going to be the natural log of 150 minus s, but when you let u equal 150 minus s, du is going to be negative ds. So it would be negative natural log of the absolute value of 150 minus s equals 1 all over 200 times t plus our constant of integration. I'm going to multiply the negative. So we would get negative t all over 200 minus c. Raising each side to the base e, we would have the absolute value of 150 minus s equals e to the negative t over 200 times e to the negative c. Now let's move up here. If we take the positive and negative of both sides, or the positive and negative of the right side, we would have 150 minus s equals our plus or minus e to the negative c times e to the negative t all over 200. We're trying to solve for s, but we are going to replace a with plus or we're going to replace plus or minus e to the negative c with a. So we would have 150 minus s equals a e to the negative t over 200. And we do have an initial condition. We know the amount of salt, S, at time 0. So let's solve for A at this point. The amount of salt is 20. Now we're looking back over here. We said the original amount of salt is 20 kilograms of salt at time 0. So we'd have 150 minus 20 equals A. Now if we plugged 0 in for t, we'd have a e to the 0. So A equals 130. So we have 150 minus s equals 130 e to the negative t all over 200. And solving for s now, we have 130 minus 150. I'm going to rearrange because this would become a positive 150 minus 130 e to the negative t all over 200. There's the solution to our differential equation. That gives us the amount of salt at time t. We want to know the amount of salt. Now this problem is given in minutes. The rates of changes are liters per minute, so we're working in minutes. So t at a half hour would be 30. Now we can solve for s, the amount of salt in the tank at a half hour. So if you were to solve this, you'd get the amount of salt is 38.1 kilograms.